So if they intersect, they have to be the same. And then the union of all the subsets has to equal the group. So we have to show two things. So let's see if we can do this. They give us a partition. So there's our hypothesis. For each r in the reals, let a sub r equal to the set of all x, y, such that x squared plus y squared equals r squared. What is that if you were thinking of a shape? A circle centered about the origin. So we're looking at these circles, and we want to show that the family of sets, a sub r, is a partition of your xy plane. Your whole xy plane, that's what r cross r is. So what we're going to do, which one do you want to show first? Mutually disjoint, or do you want to show the union of them is equal to all of the mutually disjoint? How do you show mutually disjoint? You get two sets, right? So we need an A, I'm going to call it R1, and an A R2. And this is going to be in our family of sets.
So can we use that for showing that x and y are in R1 and x and y in R2 that they all intersect? You know, if they intersect at all, they intersect everywhere, if you have to show.
We can do it that way. So let's do that. So that means such that we're going to have A R1. That didn't work. Intersected with A R2. Yeah, not equal to the intersection. Oh, it should be an R2. There we go. So AR1 intersected with AR2 is not equal to the empty set. What does that tell you?
That means the sum xy in AR1, xy is also in AR2.
Then there exists xy in AR1 and xy in AR2. How about I write it that way?
You mean to write AY?
No, that's supposed to be an xy. Right. It's in both of them, but then what does that tell us? What does it mean for xy to be in AR1?
Then x squared plus y squared is squared.
In fact, R1 squared, right? And x squared plus y squared is equal to what? R2 squared. Now, what does this tell you about your R2, R1, and R2? You know,
By the definition of
R1 squared equals to R2 squared. But what do we know about R1 and R2? They're plus or minus each other, right? Yep. So then that tells you that R1 is equal to plus or minus R2. That's not equal to. Plus or minus R2. Now, how does this help us out? We need to be able to show that the sets are the same.
So
R1 equals negative R2 with their intersection. Be the empty set?
No.
So if R1 equals R2, then we are done. So suppose that R1 is equal to negative R2, then we have to show that we're done also.
And
Which is really simple because negative root 2 squared is equal to root 2 squared.
so all we have to do actually is to be able to show set containment either direction. That's all that we're trying to do. So you're going to start with some A, B in the first set and show that it lives in the second set. So let A, B be in A, R1. I don't know how come that R is sitting there. Then what do I know? A squared plus B squared is equal to R1 squared. But I know R1 squared is equal to R2 squared, right? And thus, where does that tell you that AB lives? Go the other direction. Then what does that tell you? Yep. Is equal to R2 squared, but R2 squared is R1 squared. And what do I know? Yes. Thus, since AB, I'll write it right, in AR1 and CD in AR2 were arbitrary. What do we know?
Then it needs to be.
Well, I'm going to say that they're contained. AR1 is contained in AR2 and the other direction. Yes.
You always have to have that contained.
To show that they're equal. Thus, you know that AR1 is equal to AR2. Because we know when we square the negatives, it goes away. So, if you know they have a non-empty intersection, then they're equal. If they do not have a non-empty intersection, then they're going to be, that means they're disjoint by definition. If they have, negative, let's try that one more time. If they do not have, if they have a non-empty intersection, then they are equal sets. If they don't intersect at all, then they're disjoint. So, it follows that the set of is a family of mutually disjoint sets. Our first property show. And you show that. You assume that they have a non-empty intersection, show that the sets are equal. That's what we're going to use to show mutually disjoint. It's easier than trying to show that the intersection is empty. If you start with something in the intersection and show that it has to be the same set, that's easier to do. So that's what we do. Now what's the second thing we have to do to be able to show that this is a partition?
The union of them.
Yeah, the union is equal to the group. So that means we're showing, again, set equality. Union of all the sets equals R cross R. I know right now, just by definition, that the family of sets is contained in R cross R, right? Because we are told that X and Y was a point in R cross R, satisfying a specific value. So I know this is a subset of R cross R, so we really only have to go the other direction. We have to start with some value in R cross R, some point in R cross R, and show that it has to live in one of these A's. So we'll call it XY, be in R cross R. Then what do I know about x squared plus y squared. Yeah. Then, since the reals are closed under addition and multiplication, it follows that there exists, and we'll call it an r squared in the reals, such that x squared plus y squared equals to r squared. Does everybody follow why I can make that claim? X squared is in the reals, y squared is in the reals. The sum of that has to be in the reals. Just take the square root of that value. It too is a real number. Call it r. Then r squared is equal to that sum. If you will, we can write it this way. So that's a real value. And so, where does, it's supposed to have a square root on it. That says that xy has to live in A, and I'm going to make this be the square root of x squared plus y squared for the r, the little sub r on it. And this is an element of our family of sets. Thus, we can say that the reals crossed with the reals is contained in the family of our sets, and hence we have equality. What's our conclusion? The family of sets is a partition, right? That's the first part of the problem. You have 4 problems. They're pretty much like that. Show that things are partitions. The first part. The second part said give a geometric description. What is our geometric description? This is a set of all circles centered at the origin, right? With radius r in the reals.
I still don't understand what we did on the second half of the proof to show that the union of all of them became the set.
You have to show union both directions. So you have to show that r cross r is a subset of the family.
And then just that the family is a subset of
Yeah. Well, I should put this as a union in reality instead of just this. Union r in the reals of the family AR. Because it's in one of them, which means it's in the union of them. Yeah.
So this is saying that the r cross r
Yes.
is bigger than the other side?
Right. It's
Or
at least,
smaller than smaller
no.
because it's like-
I'm saying that r cross r is contained in here. I'm not saying it's smaller. I'm saying it lives in there. They could be equal. Because remember, I can write this. Our set 1, 2 is contained in our set 1, 2. No, it's smaller.
R cross R refers to the entire family.
Mhm.
So that was,
Mhm.
right?
Remember, your radius is going infinite. Yes, it is. But so when you show this is a subset of the union, and use bad notation here, sorry about this. Subset of the union are in the reals of the ARs. When you show that, you know the union goes the other direction, is contained in R cross R. So then that tells you that they're equal. And you have the set containment going both directions. That's how you show equality of two sets. Does that answer your question? Sort of. Let me go up here and fix this up here too. Right here. There we go.
So hard to read.
I wish they'd, you know, I keep asking them to, on the board, so hard to read, or on the screen. I keep asking them to come fix the light bulb on that and put a brighter light bulb. And they come in and they go, it's still working. So we need to burn out the light bulb. I'm recording this. And get us a new light bulb.
So you're saying the projector?
The projector's fine, it's the light bulb is dim, it's an old light bulb.
Dim? That's the
Mhm.
problem?
That's the
I
problem.
imagine if there's a way to turn off some of the lights over there.
Well, I can make us all fall asleep. You know, that's a good idea before they take the other projector out of them, because the other projector's broken.
The other thing you could do is just open the light, the thing up and shake the light over a dozen times
And then put it back in.
put it back in.
Whoa.
Not that I'm recommending that, it's just,
That's all.
it's a very simple possibility.
Yes, but I mean, look at how dark that is.
Right.
It's gonna die one of these times.
Oh,
I've been
it's dark.
complaining about this ever since we had it set there in logic at 8 o'clock in the morning in this room.
That's long.
This is the same light bulb, and it was bad then. 2 years ago. Yeah.
You get those really expensive lights.
Those light bulbs are expensive. But, yes, that was 2 years ago. We moved it. Everybody was asleep in the first 15 minutes. Everybody was. I mean, I'd have been asleep except I had to talk. Okay, so there is our problem. And that one is actually a really good test question because that's an object you can visualize in your mind. So that's a great test question for showing a partition. Okay, so that is C2.
So what are the two conditions that we have
To show that it's a partition, you have to show that all the sets in your family of sets are disjoint. That means that no two of them intersect. And we do that by assuming that two of them intersect and show that they have to be the same set. And then you have to show that the union of your family of sets is equal to the entire group.
Are you recording?
Yes. Okay, oh, I jumped too far. Then the next one I want to look at is something talking about equivalence relations. This one's going to be E5. You have to do E1, which is why we're actually going to look at E5. E1 is talking about a partition and proving that you have a partition on A cross B. But E5 is actually a great test question as well because it's dealing with equivalence relations and partitions. So we're putting things together here. Let's get our hypothesis statement. Let tilde 1 and tilde 2 be disjoint equivalence relations on A. A is a set. And we're going to define a third equivalence relation. And our third equivalence relation simply says A is equivalent to B with the third relation if and only if A is equivalent to B under both the first and the second equivalence relations. That's going to be our third equivalence
Could you
relation.
show us like a real example of what this could be? talking about?
Suppose we could say the evens is equivalent to the integers, and our equivalence relation would be e equals to 2m. So that's our function that's going to take the integers to the evens. We could say, let's see, the evens, the odd we know is equivalent to the evens. So we have some other function that takes the odd to the evens, and it would be by, an odd number is 2x plus 1. So you take your odd number, we call it O, and then we subtract 1 to get to our even. So it's going to be like O minus 1. So if you have 1 in the odds would be equivalent, well, let's go with 3 in the odds is equivalent to 1. 2. Yeah, subtract 1. 3 is equivalent to 2. Over here, from the integers, 2 is equivalent to 1. So we would have our equivalence relation between 1 and 3. We'd say 1 is equivalent to 3. Oh, no. I'm doing the transitive property. I don't want to do the transitive. I want to say I set it up for transitive property, which I'm going to use later. But I want to say if you know that A is equivalent to B under one operation, and you know A is equivalent to B under a second operation, whatever, maybe A equals to B is your first operation, and what's another equivalence relation that we've used in the past? Less than or equal to doesn't work. We had some equivalence relations from last time, guys. What were they? What was the one we did? Okay, let's see what they give. Oh, stacks of pennies in a jar. Oh, that's a partition. Let's see. Yeah. Suppose we're talking about weight for the second one. So we have two objects, and we say, you're in the grocery store and you're looking at cans. And we'll say that 2 cans are equivalent if they have white labels. Oh, no, that would perfect.
Is that a bulb or is that?
That's because this doesn't sit, this thing is broken. It's supposed to have a screw that comes out on the bottom to keep it perfectly level, and it's broken off. Okay, so if they have white labels, 2 cans are equivalent. And then we'll say that 2 cans down here are equivalent if they weigh the same thing. So our third equivalence relation is going to be if it satisfies both of them, then they're equal. So both of our cans, we pick up 2 cans, they both have white labels and they both weigh the same. Then under our third relation, they're equivalent. Does that make sense?
Mm-hmm.
Yeah.
The cans are equal or the relations are equal?
They're not equal, they're equivalent. That means that they are the same in our mind for the purposes of our discussion.
But the relation is equivalent or
We say objects in your set are equivalent under an equivalence relation. So yes, for both of them. The objects are equivalent if there is an equivalence relation between them.
So are we trying to prove?
We're trying to show that our tilde 3 is an equivalence relation. Definition of equivalence relation, it has to be symmetric, reflexive, symmetric, and transitive. Yeah. So we actually have to show that. Does that kind of make sense? Where we're headed? Did that satisfy your? It's sort of wider. Yeah.
Maybe what we need is new cable.
It's not the cableless connector. Yeah, that would work. Symmetric. Did that give you an example of what I'm talking about?
Yeah.
Yeah. Okay, so we want to satisfy the three things. We want to show the first one is reflexive. What does reflexive mean? So what we're going to do is let A be an element of our set A. And for our purposes, it's a tin can. Now tell me about A to itself under the first operation.
A is equivalent to itself.
Yes. A is equivalent to itself under that first operation and under the second, right? Because those are equivalence relations, yes. Since, let's see. So I know A is equivalent to itself here, under both of them. What does that tell us? Yeah, A is 3 equivalent to A. Do what? Oh, yeah, we missed a little equivalent sign there, didn't we? There we go. So, I know that our equivalence relation 3 is reflexive, right? Now we have to show it's symmetric. So, let B be an A, having the property that A is 3 equivalent to B. I have to start someplace. For symmetric and transitive, you have to assume equivalent goes one direction, then you have to show the other direction or add on a third equivalence. So we're going to have A is 3 equivalent to B. What does that tell us then? I know that A is 1 equivalent to B, and A is 2 equivalent to B, right?
Mm-hmm.
That's our definition.
And B is 1 equivalent to A.
Therefore, yes, exactly. We have B is 1 equivalent to A, and B is 2 equivalent to A. Which means that I have B is 3 equivalent to A, and hence our equivalence relation, the equivalence relation, is symmetric. Now we have to show it's transitive. So let C be an A such that we're going to assume A is 3 equivalent to B, and B is 3 equivalent to C. What do we know then? I know A is 1 equivalent to B, and A is 2 equivalent to B. And I know that B is 1 equivalent to C, and B is 2 equivalent to C.
And then A is 1 equivalent to C.
Yep. A is 1 equivalent to C, and what?
There's two again.
2 equivalent to C. So A has to be 3 equivalent to C. Thus, our equivalence relation, 3 equivalence relation, is transitive. Therefore, draw your conclusions. 3 equivalent is an equivalence relation on our set A.
So whenever we're proving that something's an equivalent relation, we prove reflexive, symmetric,
Intransitive, yep. And you see those popping up everywhere. We saw that in set theory and logic. I think we did that in analysis and now in abstract. Can't remember if that actually happens in geometry or not. It's been so long since I taught geometry, but I think it did. Yeah. So you're going to see that over and over again. That'll become something you kind of feel comfortable with and happy when it's that day for the topic, because you're like, I know how to do that. Okay, so there's our equivalence relation. Now, here's the last part of the question. It says, if we have an equivalence class on X, equivalence I, where I is 1, 2, and 3, prove that X3 is equal to X1 intersected with X2. So this is the second half of the proof. So we're going to let this be an equivalence relation. And we're going to show that last little bit. Notice what we have to show deals with set equality. How do you show sets are equal? Subsets of each other. So let's start with something in the equivalence class for 3, our third equivalence relation. So we're going to have A be in our equivalence class with the third equivalence relation. I need to know something about the equivalence class on the second. Let's just write down the definition. If A is in that third equivalence class, then I know that A, that's the wrong symbol. A is 3 equivalent to anything else in the set, especially the name of the set. Does that make sense? Okay. So apply our definition. It follows that A has to be 1 equivalent with X, and A has to be 2 equivalent with X. Therefore, A has to live in, that R sticking there again. A has to live in X equivalent with the equivalence class on 2, and where else does it live? Yeah, has to live in X equivalence class 1. Thus, what's our conclusion here? I know that the equivalence class for 3 is contained in the equivalence classes for 1 intersected with the equivalence class for 2. I get the intersection because of this and right here. That gives me my intersection. That makes sense? Everybody see that? Now go the other direction. So let B be in this equivalence, the intersection of these two equivalence classes. Where does that tell you that B lives? Each one of them, right? Thus, I know that B has to be 1 equivalent to X, and B has to be 2 equivalent to X. By our definition of our third equivalence, we know that B has to be third equivalent to X. I know that B is in that equivalence class. Hence, we have showed that this equivalence class is contained in the third equivalence class. What's your conclusion? Yeah. And our proof is complete. Does that make sense to you guys? Okay? You have about 20 minutes left. Start working on your homework for chapter 12. That's what you're doing in your homework. Equivalence relations and partitions on sets. And you're going to use equivalence relations to get some of your partitions, which is why they're both in this section. So go ahead, get in your little groups, start working on your homework.